Swayam Prabha. Digital India. Educated India.
Hello and welcome to our lecture today. So, we will continue, we have our last session on a discussion on test of hypothesis. Okay. So, just to briefly mention, you have the null hypothesis, you have the alternate hypothesis, you compute a test statistic, okay, and a p value. Okay. You have a rejection region, and you draw your conclusion. Okay. So, if you change any one of these clauses, then it represents a new test of hypothesis. Okay. And we have in last class we have discussed in great detail, you can either have a two-tailed test of hypothesis or a one-tailed test of hypothesis. Okay. So, for a two-tailed test of hypothesis, for a two-tailed test, okay, z value. Okay. So, this is the rejection region. Okay. And here H naught is true. So, this is the acceptance region. Okay. So, these values or the critical values are referred to as z of alpha by 2. Okay. So, choice of z of alpha by 2 is dependence on the confidence in the level of significance. So, level of significance dictates the value of z of alpha by 2. Okay. And what we know is for 0.5 or alpha, alpha is nothing but the total area under the curve. So, both of these areas are alpha by 2. Okay. Alpha is 0.5, z of alpha by 2 is 1.96. Okay. And for the one-tailed test, okay. So, here in case of two-tailed, my null hypothesis is mu is equal to mu naught and HA is mu naught equal to mu naught. Okay. For the one-tailed, my H naught is mu equal to mu naught and HA is mu is greater than mu A or mu less than mu A. Sorry, mu naught. Okay. And for the one-tailed test, you are only concerned about this area. Okay. So, you call this as z alpha, and you depending on the value of alpha, you can accordingly change the value of z alpha. Okay. So, this error that you accumulate, okay, okay, minus, okay, this area under this curve is alpha by 2. So, the net area is alpha. So, alpha represents the probability, okay, the net probability of rejecting, okay, H naught when it is true. Okay. So, but alpha you have some control over. So, this is called a type 1 error. Which means that you can reject H naught when it is still true. But there is an alternate possibility of called a type 2 error. This, okay. So, and beta is the probability of accepting H naught when it is false. Okay. So, you would imagine that the true effectiveness of a test, okay, the true effectiveness of a test will depend on both of your choices of alpha and beta. Okay. So, if I were to write down this plot again, okay, let us say you have H naught is true or H naught is false, and you have a decision. Okay. If you accept that H naught is true, so this is correct, but this is called a type 2 error. Okay. If you reject, if your final decision is reject, this is your type 1 error, and this is correct. Okay. So, there are two types of errors you can make. This is your type 1 error and this is your type 2 error. So, probability of type 1 error is alpha and probability of type 2 error is beta. Okay. Now, what you see alpha, this is in the statistician's hands or experimentalists. Can control. Why? You can choose alpha equal to either 0.01, 0.05, 0.001, so on and so forth. So, this is in your hands, but it is very difficult to choose beta. Why? Because beta is your type 2 error, which is that you are accepting H naught when it is false. So, your choice, your H naught is mu equal to mu naught, right. If your H naught is false, you have no idea of what the value of mu is. So, how can you go about setting the value of beta? Okay. So, this is very difficult to know. So, for a good test, okay, for a good test, both alpha and beta should be small. Okay. Now, I can calculate 1 minus beta, okay, which is nothing but probability of rejecting H naught okay. So, rejecting H naught when it is false. Okay. And this, okay, this is called the power of the test. And you can generate 1 minus beta as a function of mu a, and this curve is called a power curve. Okay. Let us see what we can say about beta or 1 minus beta. Okay. So, let us take an example. Let us go back to the example where we found was 880 tons was the weekly average. Okay. Weekly average earlier known. Okay. Now, okay, for let us say So, the control manager does the statistics, okay, does the statistics and finds, okay, that x bar equal to 870. Okay. Okay. So, we want to calculate, okay, beta. Okay. Okay, we want to calculate beta, okay, for this case. Now, what we know, okay, so my null hypothesis is mu equal to mu naught, okay, and this mu naught is 880 tons. Okay. So, mu is equal to 880, and from previous cases we had seen S was 21, N was 50. Okay. So, we calculate, okay, Z equal to x bar minus mu naught, okay, by S by root n. Okay. So, if you were to reject your H naught, okay, so if you were to reject your H naught, so this Z you can calculate the value to be, okay. So, for, let me draw it again. Okay. So, what is your H naught for alpha equal to 0.5? Let us say alpha equal to 0.05. Okay. For your two tail test, this value is 1.96. Okay. So, in order to accept your H naught, your Z has to, so for accepting H naught, my Z must be bound by, okay. So, because this is my accept H naught area, okay. This is the range over which I am going to accept my null hypothesis. Okay. So, if you plug in the values, so if you write down minus 1.96 less than x bar, okay, minus 880 by 21 by root 50, okay, less than 1.96. So, if I plug in the values, I will get a range of 874.18 less than x bar less than 885.82. Okay. But what I know, okay, this is if H naught was true, but what I know, my mu is equal to 870, which is not equal to mu naught. Okay. So, I can calculate the test statistics Z1 and Z2, which is given by x bar minus 870 by 21 by root 50, and Z2 equal to x bar minus 870. Okay. So, okay. So, I can, so using this expression I can plug in these values, okay. I can find out corresponding to 874.18, okay, 50, I get Z1 equal to 1.41 and Z2 is 885.82 minus 870 by 21 by root 50. Okay. This gives me a value of 5.33. Okay. So, if I were to draw this curve together, okay, slide it. Okay, this is H naught equal to true. Okay. This is centered around 870. Okay, this is H A equal to true. That mu is not equal to mu naught. Okay. What I know is my acceptance range. Okay. This I calculated at 874.18 and 885.82. Okay. This is my alpha. Okay. So, I can, this is my alpha by 2 and this area is my alpha by 2. Okay. But I can extend this point high up, okay, and calculate. So, if I draw this line again, okay, I can calculate this total area under this part of the curve. Okay. This has to be beta. Why? Because beta, okay, beta is probability of accept H naught when mu equal to 870. Okay. Beta is equal to probability of accept H naught when mu equal to 870. Okay. So, my beta is equal to probability, okay, 1.41 less than Z less than 5.33. Now, 5.33 is way too far from here. So, for all practical purposes I can write probability of Z greater than 1.41 and this probability comes out to be 0.08, roughly comes out to be 0.08. Okay. So, then I can write 1 minus beta is 0.92. Okay. So, this tells you, okay, the probability, okay, the probability of collectively rejecting H naught when mu is true, okay, is 92%. Okay. Probability of, again, probability of rejecting H naught when HA is true is 92%. Okay. Now, one more thing you observe from this curve. Okay, let me redraw this curve once more. Okay. Okay. Let me draw two curves. Okay. Let us say this is my alpha. Okay. This area is alpha by 2. I extend it and this area is beta. Okay. What can I say about my choices of alpha and beta? Okay. Are alpha and beta linked by any choice? So, what you can clearly see from this curve is if I increase my alpha. So, let us say if I had chosen alpha prime, okay, equal to this, let us say this is my alpha prime by 2. Okay. Then correspondingly this area is going to be beta prime. Okay. So, this implies that if alpha is increased, beta decreases. Okay. But if you want to prescribe keep your alpha as constant, what should be the strategy for decreasing beta? Right, you want to decrease both alpha and beta. Okay. So, what I want to do is, if this is my curve for alpha, okay, so imagine I want to keep alpha fixed. Okay. Alpha is constant. So, this is alpha by 2, okay, this is constant. So, I can draw a curve, okay, which is this one. Or I can draw a curve, okay, because the spread of this is dictated. So, you know your standard deviation SE, standard error is S by root of n, right. So, if you increase your sample size, then this will keep on decreasing, that for the same value of alpha you keep on reducing the value of beta. So, this tells you how you might be able to increase, like for lower value of alpha you can even decrease beta by increasing the sample size. Okay. Now, let us see for finding out the difference between population means. Mu 1 and mu 2. Okay. What should be your null hypothesis your null hypothesis can be something like mu1 minus mu2 equal to d naught, where d naught is some prescribed value that you control. Okay. And your alternate hypothesis is for a two-tailed distribution, you have mu1 minus mu2 not equal to d naught. Okay. Let us take an example. So, imagine, so you want to test, okay, so on campus, two populations of students, okay, those who own bicycles or bikes and those who do not own. Okay. And your agenda is to see whether there is any correlation, okay, with academic performance, okay, and whether there is any correlation with academic performance. So, what you are given, okay, let us say you have n equal to 100 for both, okay, x1 bar is 2.7, okay, x2 bar is 2.54, s1 square is 0.36, s2 square is 0.4. So, is there any significant difference in their academic performance? Okay. So, for addressing this, so you just want to know whether there is a difference in their academic performance or not, which means that in our case, this particular case, so this example continued, we want to choose d naught equal to 0. Okay. You choose d naught equal to 0. Okay. So, your h naught is mu1 minus mu2 equal to 0 and h a is mu1 minus mu2 not equal to 0. Okay. So, in the general case, z, the test statistic, has to be defined as since for this particular case our d naught is 0, okay, we can simply put in these values. Okay, and you get a value for the test statistic as 1.84. Okay. So, how will you know whether this is significant or not? So, corresponding to alpha equal to 0.05, okay, you are doing, okay, a two-tailed test, right, a two-tailed test. So, z of alpha by 2 is 1.96. Okay. So, since z is not greater than 1.96, I will say h naught is not rejected. And this is also clear by computing the p value. Okay. The p value turns out to be probability of z is greater than 1.84 plus probability z is less than minus 1.84. Okay. And this you get a value of 0.0658. Okay. So, what you see is you can reject. So, this is possible to reject, okay, h naught at 0.1 level of significance. Okay. So, in this case you do not reject H naught, okay. Don't reject. So, we do not reject H naught. Okay, we don't so we can reject H naught at 0.1 level of significance. At 0.05 level of significance, we do not reject H naught. Okay. So, and you can see that if you calculate the 95% confidence interval, okay, the 95% confidence interval comes out to be x1 bar minus x2 bar plus minus 1.96 times SE, which is root of S1 square by N1 plus S2 square by N2. Okay. This comes out to be 0.16 plus minus 0.17. So, the bounds become minus 0.01. Okay. So, because it is possible to have a value of 0, that is no difference, or 0.2, which is greater, or minus 0.01. Okay. So, that is why you see that you cannot reject, you cannot say that there is statistical difference between these two populations. Okay. Let us do one more example. Okay. So, regardless of age, okay, in a community, okay, 20% adults participate in fitness activities, okay, fitness activities twice a week. Okay. So, and this frequency drops with age. Okay. This drops with age. Now, let us say in a sample of n equal to 100 adults, okay. So, what you find, adults over 40 years of age, age 15 people stated that they exercise at least twice a week. Okay. So, does this indicate participation of adults greater than 40 is significantly less than 20%. Okay. So, what you are given in this problem, so 20%, so you have a problem about proportions. Okay. Your null hypothesis HO is P equal to P naught equal to 0.2, and your alternate hypothesis is P less than 0.2. Okay. So, your proportion, okay, proportion P hat, say we know it follows normal distribution with mean P naught, okay, P naught, and standard error root of P naught Q naught by n. So, but in your case, so in your specific case, you know p hat is 15 out of 100, which is equal to 0.15. So, if you calculate the z statistics, okay, it is 0.15 minus 0.2 to minus 1.25. Okay, so the p value comes out, okay, to probability of z less than minus 1.25. Okay, and this is 0.1056. So, this would tell you that your evidence is insufficient. Okay, this would tell you that your evidence is insufficient. Okay. So, this also brings us to another point, that how do you make a difference, or how do you make a difference between statistically significant versus practically important. Okay. How do you make a difference between statistically significant and practically important? So, in the above case, okay, whatever this case you calculated, if let us say you increased your n equal to 400, okay, then your p value becomes 0.0062, because your z becomes minus 2.5. Okay, so, now it is significant, but it may not always be practically important. For this, you need to see your specific case. For example, if I want to see, so yeah, I have a cell, a cancer cell which kind of is invasive, and I have drug D, okay, which targets this, its ability to invade. Okay. So, if you measure its motility, okay, so imagine you have a plot like this. Okay. So, there is, as you can clearly see from this plot, there is very little difference between the control group and your drug group. But sometimes, let us say, if I were to draw in a different case, okay. Okay. So, what the drug has done is the extent of variation in the population is reduced, but the mean has not changed, okay, or it has just shifted slightly to the left or up or down. Okay. So, even though this is might be statistically significant, it may not hold any practical importance. So, this has to be exercised at the on a case by case basis. With that, I thank you for your attention, and I look forward to next class. Okay. In the next class, we will start discussing about the t-test, the student's t-test. Thank you.